My name is Hongbo. Today, I and my collaborator, Chen, are honored to present our work, a new verification framework for confidential computing. Our work focuses on a fundamental challenge: how can we trust the software running in secure enclaves? Agora's design features trustless and open mode. We'll explain how we achieve these two goals. Let me get started with a quick review of confidential computing. It relies on hardware-based trusted execution environments, or TEEs, to protect sensitive data while it's being processed. TEEs provide encryption and isolated execution, meaning that we only need to trust the hardware, not the host operating system or hypervisor. Remote attestation gives us a way to verify integrity of the code running inside the T. But this also brings us a critical question. Is code integrity enough? Simply putting code into a T doesn't automatically make it secure. Attestation confirms what code is running, but it doesn't tell anything about its behavior. We're often interested in deeper security properties like fault isolation, information flow control, or side channel resistance. Unfortunately, existing verification techniques have significant drawbacks. They often result in a large trusted computing base, or TCB. Also, they are tied to specific security policies and rely on a closed ecosystem of tools, which limits our ability to outsource verification. Let's look closer at problems with existing verifiers. A major issue is the big TCP problem. General purpose tools like Anger are powerful, but they are also massive. We're talking about tens of thousands of lines of code for the analysis engine and hundreds of thousands for the underlying SMT solver. Even well tested tools have bugs and vulnerabilities. And if we need to verify multiple security policies, the TCP just keep growing. The second major problem is the closed nature of the current verification ecosystem. We're forced to trust a small set of well-known tools and solvers. This makes it difficult to incorporate new, cutting-edge verifiers from the research community without blindly trust them. Our goal is to break open this closed model and create a verification framework that is both trustworthy and open.
The first innovation of Agora is to move the complex proof generator, such as static program analysis and logic-based proof system, out of the TCB. This diagram illustrates a canonical approach, which simply runs the verification workflow into TEE. Based on the policy, the program analysis generates a series of assertions for the binary to be verified. Such assertions are facts related to security properties. Such generated assertions is then sent to a trusted SMT solver, which then derives the verification result. The verifier finally signs the binary for releasing. Usually, to verify one policy, a dedicated verification framework is required. This can bloat the TCP size easily. Our first key design principle in Agora is to move the complex program analysis out of the TCB. Instead of trusting the analysis, we treat its output, that is, a set of assertions, as untrusted. We then use a much smaller trusted validator to check these assertions. The core idea here is that verifying a proof is significantly easier than generating it. This allows us to leverage powerful, untrusted analyses without expanding our trust base. To illustrate this, let's look at a case study with conf-LLVM, a compiler that enforces a coarse-grained information flow control policy. Conf-LLVM uses type annotations to label sensitive data and then compiles the code to ensure that private and public data are stored in separate memory regions. They essentially state that any instruction accessing memory must use the correct segment registers, GS for private data and FS for public data. Moreover, it encodes the sensitivity of function arguments into a magic sequence to ensure correct information flows through function calls. The key takeaway here is how the security policy is encoded into the binary. For a policy like the one in conf-LLVM, the assertions are relatively straightforward. An untrusted information flow analysis performs a complex label inference and generates assertions. Then, the validator's job is to simply check that every memory access in the binary follows this rule. This validation logic is incredibly simple, requiring only a few hundred lines of code, replacing the large and complex program analysis. But what about other security policies? We don't want to build a new validator for every policy. This brings us to our second key design innovation, a generic policy agnostic assertion language. This language allows us to express a wide range of security policies, from software fault isolation to side channel mitigations, without having to change the core validator itself. Here you can see the grammar for our assertion language. It is expressive enough to capture the low-level details of program execution, allowing us to define complex security policies in a standardized way. The language is also designed to be extensible so we can add new predicates as needed to support future policies.
Before moving to the last key design, let me introduce blockchain and smart contracts shortly. Blockchains provide a decentralized and transparent ledger, and smart contracts allow for self-executing agreements. This model of transparent and verifiable computation is a key building block of Agora. We moved program analysis out of the TCB, but what about the SMT solver? This is often the largest and most complex part of any verification toolchain. Our third key innovation is removing the SMT solver from the TCB entirely. We do this by reframing the problem. Instead of trying to prove a property is true, we challenge external bug hunters to find counterexamples. If they can find a set of inputs that violates a property, they can submit it and win a bounty. The insight here is a checker is much simpler than a full-fledged SMT solver, which dramatically reduces the TCB. Of course, designing such a system has its challenges. A key issue is measuring the effort of bug hunters when no bugs are found. To solve this, we introduce a fabricated tasks with known solutions and small rewards, and mix them in with genuine tasks. This ensures hunters must actually work on problems to claim any reward. To provide a baseline level of assurance, we can also run reference solvers. Finally, the entire process is managed by blockchain-based smart contract, which provides auditable confidence in the results, even though they came from untrusted sources. We have implemented a prototype of Agora. This includes a banner verifier, a certain validator, and the smart contract for the bug bounty system. We also have developed untrusted assertion generators for three different security policies. The entire project is open source and available on GitHub. Now for the results. The circle part compares the TCP size of Agora to another verifier. As you can see, our trusted components, especially the banner verifier and bounty task manager, are almost two orders of magnitude smaller than their counterparts in a general purpose framework like Anger. This demonstrates the effectiveness of our trustless approach. More importantly, look at the policy-specific code. To verify SFI, Agora requires only 625 lines of code, whereas a dedicated verifier like VeriVas needs almost 2,000. For information flow control, it's a 335 lines for Agora versus a 1,000 plus 500 lines for ConfVerify. This demonstrates that our generic framework is not only smaller but also more efficient for adding new policies. Moreover, we can support verification of an LVI mitigation in only 77 lines. We get strong security guarantees with a dramatically smaller trusted computing base. To evaluate Agora's correctness and versatility, we implemented verifiers for three distinct security policies. First, for software-based fault isolation, or SFI, we successfully verified binaries from the entire spec 2006 benchmark. Our results matched those of specialized tools like VeriVas, proving that our general framework doesn't sacrifice capability. For information flow control, we tested Agora on real-world systems, including Nginx and OpenLDAP, and successfully verified them. More critically, we also ran negative tests. We intentionally tampered with binaries by altering magic sequences and segment registers to create data leaks. Agora correctly identified every single violation and rejected the malicious binaries. Finally, we verified the mitigation for load value injection attacks, successfully confirming that the policy was enforced correctly across the Spec 2006 benchmark. Together, these results show that Agora is a correct, robust, and flexible verification system. Thanks a lot and hope you enjoyed the talk. Please let us know if you have any questions. To summarize, Agora is a novel verification service engineered for confidential computing environments, specifically designed to address the major problems of the large TCP. We achieved minimal TCP by offloading traditional complex components, namely static program analysis and large SMT solvers, outside of the trusted boundary. Instead, we rely on a lightweight validator and a checker for outsourced results, embodying the principle that checking a proof is easier than constructing.
Oh, ended. All right. So I believe the author is online. So if you have any question to ask, the author can hear you, I believe. Well, I guess I can ask a question since they're online. But if they're offline, then we'll go to the next one. Are they really online?
Yes, we are here.
All right, just a simple question. When you verify the result using a bug bounty, you mean human-based bug bounty, or you're using a metaphor for this?
Could you please repeat the question?
Yeah.
So you remove the Z3, right, from the TCP, and you designed a blockchain-based bug bounty system to challenge. So you mean really the human-based bug bounty system, right?
Yes, exactly.
So why not just using some kind of trusted encryption-based communication between the constraint solver and for verification of the results? I'm curious why using a human-based bug bounty verification mechanism.
Yeah, so I guess I can take this. I guess we already discussed this in the paper and in the earlier slides in the presentation. So SMT solvers or theorem provers in general has flaws. They have bugs that can invalidate the results. So we do use them as reference, like bug bounty hunters, but we don't fully trust them. That's the main reason for introducing human, actually not exact human bug hunters. Really, they are just more instances of solvers. Like you can introduce hundreds or thousands of different solvers, like distributing the computation power needed to verify a binary.